In telecommunications, a communications protocol is a system of rules that allow two or more entities of a communications system to transmit information via any kind of variation of a physical quantity. These are the rules or standard that defines the syntax, semantics and synchronization of communication and possible error recovery methods. Protocols may be implemented by hardware, software, or a combination of both. Communicating systems use well-defined formats for exchanging messages. Each message has an exact meaning intended to elicit a response from a range of possible responses predetermined for that particular situation. The specified behavior is typically independent of how it is to be implemented. Communications protocols have to be agreed upon by the parties involved. To reach agreement, a protocol may be developed into a technical standard. A programming language describes the same for computations, so there is a close analogy between protocols and programming languages. Protocols are to communications as programming languages are to computations. Communicating systems. The information exchanged between devices, through a network, or other media, is governed by rules and conventions that can be set out in technical specifications called communications protocol standards. The nature of a communication, the actual data exchange and any state-dependent behaviors, is defined by its specification. In digital computing systems, the rules can be expressed by algorithms and data structures. Expressing the algorithms in a portable programming language makes the protocol software operating system independent. Operating systems usually contain a set of cooperating processes that manipulate shared data to communicate with each other. This communication is governed by well-understood protocols, which can be embedded in the process code itself. In contrast, because there is no common memory, communicating systems have to communicate with each other using a shared transmission medium. Transmission is not necessarily reliable, and individual systems may use different hardware and/or operating systems. To implement a networking protocol, the protocol software modules are interfaced with a framework implemented on the machine's operating system. This framework implements the networking functionality of the operating system. The best-known frameworks are the TCP/IP model and the OSI model. At the time the Internet was developed, layering had proven to be a successful design approach for both compiler and operating system design. Given the similarities between programming languages and communications protocols, layering was applied to the protocols as well. This gave rise to the concept of layered protocols, which nowadays forms the basis of protocol design. Systems typically do not use a single protocol to handle a transmission. Instead, they use a set of cooperating protocols, sometimes called a protocol family or protocol suite. Some of the best-known protocol suites include IPX, SPX, X25, AX25, AppleTalk and TCP/IP. The protocols can be arranged based on functionality in groups. For instance, there is a group of transport protocols. The functionalities are mapped onto the layers, each layer solving a distinct class of problems relating to, for instance, application, transport, internet and network interface functions. To transmit a message, a protocol has to be selected from each layer, so some sort of multiplexing, demultiplexing takes place. The selection of the next protocol is accomplished by extending the message with a protocol selector for each layer. Basic requirements of protocols. Messages are sent and received on communicating systems to establish communications. Protocols should therefore specify rules governing the transmission. In general, much of the following should be addressed. Data formats for data exchange. Digital message bit strings are exchanged. The bit strings are divided in fields and each field carries information relevant to the protocol. Conceptually, the bit string is divided into two parts called the header area and the data area. The actual message is stored in the data area, so the header area contains the fields with more relevance to the protocol. Bit strings longer than the maximum transmission unit are divided in pieces of appropriate size. Address formats for data exchange. Addresses are used to identify both the sender and the intended receiver. The addresses are stored in the header area of the bit strings, allowing the receivers to determine whether the bit strings are intended for themselves and should be processed or should be ignored. A connection between a sender and a receiver can be identified using an address pair. Usually some address values have special meanings. An all-1s address could be taken to mean an addressing of all stations on the network, so sending to this address would result in a broadcast on the local network. The rules describing the meanings of the address value are collectively called an addressing scheme. Address mapping. Sometimes protocols need to map addresses of one scheme on addresses of another scheme. For instance, to translate a logical IP address specified by the application to an Ethernet hardware address. This is referred to as address mapping. Routing. When systems are not directly connected, intermediary systems along the route to the intended receiver need to forward messages on behalf of the sender. On the Internet, the networks are connected using routers. This way of connecting networks is called internetworking. Detection of transmission errors is necessary on networks which cannot guarantee error-free operation. In a common approach, CRCs of the data area are added to the end of packets, making it possible for the receiver to detect differences caused by errors. The receiver rejects the packets on CRC differences and arranges somehow for retransmission. Acknowledgement of correct reception of packets is required for connection-oriented communication. Acknowledgements are sent from receivers back to their respective senders. Loss of information, timeouts and retries. Packets may be lost on the network or suffer from long delays. To cope with this, under some protocols, a sender may expect an acknowledgement of correct reception from the receiver within a certain amount of time. On timeouts, the sender must assume the packet was not received and retransmit it. In case of a permanently broken link, the retransmission has no effect, so the number of retransmissions is limited. Exceeding the retry limit is considered an error. Direction of information flow needs to be addressed if transmissions can only occur in one direction at a time, as on half-duplex links. This is known as media access control. Arrangements have to be made to accommodate the case when two parties want to gain control at the same time. Sequence control. We have seen that long bit strings are divided in pieces, and then sent on the network individually. The pieces may get lost or delayed or take different routes to their destination on some types of networks. As a result, pieces may arrive out of sequence. Retransmissions can result in duplicate pieces. By marking the pieces with sequence information at the sender, the receiver can determine what was lost or duplicated, ask for necessary retransmissions and reassemble the original message. Flow control is needed when the sender transmits faster than the receiver or intermediate network equipment can process the transmissions. Flow control can be implemented by messaging from receiver to sender. Getting the data across a network is only part of the problem for a protocol. The data received has to be evaluated in the context of the progress of the conversation, so a protocol has to specify rules describing the context. These kind of rules are said to express the syntax of the communications. Other rules determine whether the data is meaningful for the context in which the exchange takes place. These kind of rules are said to express the semantics of the communications. Formal specification. Formal ways for describing the syntax of the communications are abstract syntax notation 1 or augmented Bacchus NAUR form. Finite state machine models and communicating finite state machines are used to formally describe the possible interactions of the protocol. Protocols and programming languages. protocols are to communications what algorithms or programming languages are to computations. This analogy has important consequences for both the design and the development of protocols. One has to consider the fact that algorithms, programs and protocols are just different ways of describing expected behavior of interacting objects. A familiar example of a protocoling language is the HTML language used to describe web pages, which are the actual web protocols. In programming languages, the association of identifiers to a value is termed a definition. Program text is structured using block constructs, and definitions can be local to a block. The localized association of an identifier to a value established by a definition is termed a binding, and the region of program text in which a binding is effective is known as its scope. The computational state is kept using two components: the environment, used as a record of identifier bindings, and the store, which is used as a record of the effects of assignments. In communications, message values are transferred using transmission media. By analogy, the equivalent of a store would be a collection of transmission media, instead of a collection of memory locations. A valid assignment in a protocol could be Ethernet equals message, meaning a message is to be broadcast on the local Ethernet. On a transmission medium there can be many receivers. For instance, a MAC address identifies an Ethernet card on the transmission medium. In our imaginary protocol, the assignment Ethernet MAC address equals message value could therefore make sense. By extending the assignment statement of an existing programming language with the semantics described, a protocoling language could easily be imagined. Operating systems provide reliable communication and synchronization facilities for communicating objects confined to the same system by means of system libraries. A programmer using a general-purpose programming language can use the routines in the libraries to implement a protocol, instead of using a dedicated protocoling language. Universal protocols. Despite their numbers, networking protocols show little variety, because all networking protocols use the same underlying principles and concepts. In the same way, the use of a general-purpose programming language would yield a large number of applications only differing in the details. A suitably defined protocoling language would therefore have little syntax, perhaps just enough to specify some parameters or optional modes of operation, because its virtual machine would have incorporated all possible principles and concepts, making the virtual machine itself a universal protocol. The protocoling language would have some syntax and a lot of semantics describing this universal protocol, and would therefore in effect be a protocol, hardly differing from this universal networking protocol. In this context, a protocol is a language. The notion of a universal networking protocol provides a rationale for standardization of networking protocols, assuming the existence of a universal networking protocol. Development of protocol standards using a consensus model might be a viable way to coordinate protocol design efforts. Networking protocols operate in very heterogeneous environments consisting of very different network technologies and a very rich set of applications. So a single universal protocol would be very hard to design and implement correctly. Instead, the IETF decided to reduce complexity by assuming a relatively simple network architecture, allowing decomposition of the single universal networking protocol into two generic protocols, TCP and IP, and two classes of specific protocols, one dealing with the low-level network details and one dealing with the high-level details of common network applications. ISO choose a similar but more general path, allowing other network architectures to standardize protocols.